In this lesson, we're going to talk about estimating areas under a curve with something called the trapezoidal rule or the trapezoidal approximation. I'm also going to do one approximation with Riemann sums. So the trapezoidal approximation, very similar to Riemann sums, you will estimate area by dividing the region into geometric shapes. However, instead of rectangles where we raise up and we go straight across horizontally, either left point, right point, or through midpoints, with trapezoids we connect the points on the curve with the line, which ends up creating a trapezoid. Remember, a trapezoid, back to just reviewing the area of a trapezoid has two parallel sides. Those are the bases. The distance between those parallel sides is your height, and so there's your formula for the area of a trapezoid. The trapezoids we are looking at are standing up on end. The bases are the parallel sides, which are vertical, and the height of our trapezoid is the change in x from one x coordinate to the other. So our trapezoids look like this, where we have the bases vertically and the height is horizontal. And when I find the area of one of those trapezoids, so if I look at this very first one, that area is going to look like this. So I'm using T sub n to represent a trapezoidal approximation with n subdivisions. So my first trapezoid, it's 1/2 times the height, but the height of the trapezoid is the distance between the x's, so that's your delta x. And then the bases would be the y coordinates of these 2 points on the curve up here. So the length of these two bases is that y coordinate, so I have to plug in my x's to get the y's. So half delta x, f of x0 plus f of x1, there's our first trapezoid. My next trapezoid, if I move over, is going to be half the height times the sum of the bases, and the bases are f of x1 and f of x2, and we could carry that all the way across until we get to the very last, and we're going to pretend we cannot count these subdivisions. So we go from my third x coordinate right here, my third subdivision, we're going to pretend we can't count those, and we're ending with some unknown number of subdivisions, x sub n. So we could break it up and do a whole bunch of individual trapezoids. However, if your delta x's are the same, we could do a little bit of algebra to this, and you'll notice that each one of these areas has a 1/2 delta x in common. So I could factor out the 1/2 delta x. I'm factoring that out. And when you factor that out, you'll see that there's an f of x sub 0, then there is a f of x sub 1 plus another f of x sub 1, and there are two of those. F of x1, f of x1. There are also two f of x2s. Everything on the interior, all of these vertical pieces in the middle, like this base right here, is shared with two trapezoids, so we have two of those bases. And with a little bit of algebra, we end up with a nice cleaned up trapezoidal approximation formula that looks like this. It's your delta x over 2, or half your delta x, and then we have 1 f of x sub 0, your initial x coordinate. There's 1 at the very end, but there are 2 of every x coordinate in the middle. And this thing right here is your trapezoidal rule. If you look in a textbook, you'll probably see this in a box somewhere at the beginning of the section. So there is your approximation method using trapezoids. Most people are okay just memorizing this rule and not really worrying about where it came from. However, I feel there's a little bit of value in seeing where those formulas come from. So let's put this into practice. First with a real function, I say real function, a function that is known. We actually have an equation for this function. So we're using f of x to be e to the negative x squared. We are going from 0 to 3 using trapezoids and 3 subdivisions of equal length. And the equal length is important because if they are of equal length, then the height of your trapezoids, which is your delta x, is still b minus a divided by n, and my delta x is 1 here. So I like to draw my x-axis. I'm starting at 0. I'm stepping up by 1s. And I'm ending at 3. And so here's where I start. I start at 0. I end at 3. So my trapezoidal approximation with 3 subdivisions is going to be my delta x, which is 1, divided by 2, times 1 f of your initial value, so f of 0, plus everything in the middle happens twice. So we have 2 f of 1. We have 2 f of 2. And then you have to remember that the last x coordinate is the base for only one of the trapezoids, that very last one. And so we have 1 f of 3. And on ugly problems like this, where you have a weird function, like I don't know what the value of e to the negative 4 is if I were to plug in 2 for x. So these are very commonly calculator questions if it's presented in this format. So I'm going to just slide the calculator up here, the calculator answer up here. You can see what we get. And there we have our answer of 0.8862. And on the AP exam, if you are in AP Calculus, 0.886, always 3 decimals. You'll see that in my calculator, I stored my function, my equation in F1, and then I went to my compute screen, and then I just referred to my F1, make it a little bit easier to plug in. So the next type of problem is one where we do not have an explicit formula, and instead they give you a table of values and ask you to approximate the area under this curve. So here we have a table of values f of x. It does mention that f is continuous, and so to estimate this area, what I would like to do, we're going from 1 to 7, that's a total length of 6, so I would like to think that my delta x is 7 minus 1, and it does ask you to use the 3 intervals, so I'm going to divide by 3, and that will give me a delta x of 2, and so you might be thinking this right off the bat. We're doing trapezoids, so my delta x is 2 divided by 2 times f of my first x coordinate, if I'm starting at 1, f of 1, and if my delta x is 2, my next x coordinate would be 3, which is cool. My next x coordinate would be 5, and here's where we have an issue, because this problem, we don't have information for 5. It falls somewhere between 4 and 7, and so because of the way this problem is presented, we cannot go to the memorized formula for the trapezoidal approximation, and the problem does say use the 3 intervals indicated by the table. You are not allowed to create your own information to complete the problem. So this method fails, and what we have to do this time is we actually have to find the areas of 3 separate trapezoids. We cannot use a memorized formula, and so the area of a trapezoid, you have to remember, is 1/2 the height of the trapezoid times the sum of the bases. And the height of your trapezoid is the change in x. So I'm looking at this table, and I go from an x of 1 to an x of 3. That is a distance of 2. Then I go from an x of 3 to an x of 4. That's a distance of 1. And 4 to 7 gives me a distance of 3. Those are the heights of the 3 trapezoids. And the function values are the length of the bases. So when I do my trapezoidal approximation, this area is going to be approximately half the height of my first trapezoid, which is 2, times the sum of the bases, which are 2 and 5 for that first trapezoid. Plus, then I go to my next trapezoid. Half the height, my height of my next trapezoid is 1, and the bases of my next trapezoid are 5 and 3. So 5 plus 3 plus, and then my last trapezoid, half the height of my last trapezoid, which is 3, and the sum of the bases would be 3 and 9. So 3 plus 9. And if it's a free response question on the AP exam, you must write it out this way. They want to see the full trapezoidal representation, which means you are adding bases. Do not skip writing 2 plus 5 and go straight to 7 or straight to 8 or straight to 12. And I would probably leave my answer like this if it were a free response question, because you are allowed to stop as soon as you have only arithmetic left. But for fun, I am going to add these together and simplify this, and we would get a final answer of 29. Alright, so there we go. We get an answer of 29, or if it's free response on the AP exam, AP Cal exam, you can stop with this ugly line right here. So we have one more problem to look at. And this problem is the exact same one we just did. Same table, same intervals, and this software is frozen, so hold on. There we go. So the table and everything is the exact same, only this problem, we're using the 3 intervals with a right-handed Riemann approximation. And again, because the delta x is not the same as we march our way through the data here, we go up by 2, then we go up by 1, then we go up by 3. When you have an inconsistent or inconsistently spaced intervals, then you have to treat this as three separate rectangles rather than using some memorized formula. So this area approximation is going to be my first rectangle. The base of your rectangle is the delta x, so that would be 2 times, and we are using the height of the rectangle determined by the right side, and so on this first interval, the right side is here, and the height is the function's value of 5. So there's my first rectangle. My next rectangle from 3 to 4 has a base of 1, and the right side of that interval is, where'd my cursor go? Okay, there we go. The right side of that interval is at the height at 4, which is 3. So that will be 1 times 3. And then my very last rectangle from 4 to 7, that rectangle will have a base of 3. That's your delta x. And then the height of that rectangle, is going to be 9. Sorry if this is sounding really jumbled up. I'm having to pause this recording a lot because the software keeps freezing on me. So so we had a base of 2 with a height of 5 for my first rectangle, a base of 1, your delta x, with a height of 3 for that rectangle, and then my last rectangle from 4 to 7, a base of 3 and a height of 9, because that is the y coordinate on the right side of that interval. And then if it's free response, just like before, you can leave it like this. If it's a multiple choice question, you would have to clean this up. So that'll be 10 plus 3 plus 27, which would give you an area of 40. So there you go. There is a Riemann approximation with the table, and then the trapezoidal approximations with a table and with a known function. But lately on the AP exam, they have been asking these types of questions with tables more so than they have with a known function.